Welcome. Today we are going to solve another three problems in control systems. So the first question is that the unit impulse response of a linear time invariant system is the unit step function. For t greater than 0, the response of the system for an input of e power minus 4t u of t will be. So from this problem, they have given that the impulse response of the LTI system h of t is u of t. That is, u of t is the unit step function. I'll just describe you with a block diagram. So this is the impulse response. They are feeding the system with a unit impulse function and you are getting the output as unit step function. So they have given the impulse response and they are asking the output y of t for the given input r of t for the same LTI system. So the impulse response is denoted by h of t here. So which is given by the unit step function. Taking Laplace transform, h of s is equal to 1 by s. So taking Laplace transform of unit step function is 1 by s. R of t is given as e power minus 4t u of t. Taking Laplace transform, we get R of s equal to 1 by s plus 4, which you can find it from Laplace transform table. So the output y of s is given as h of s into r of s, which is 1 by s into 1 by s plus 4. So this is y of s. Before we take the inverse Laplace transform, we'll just apply the partial fraction method for simplification. So this can be separated like this using partial fraction method, that is equal to a into s plus 4 plus bs divided by s into s plus 4. So these two cancel each other, a into s plus 4 plus bs. So we have to solve this problem, solve this equation. So equation 1 can be solved to such that we can find a and b separately. For making this term as 0, put s equal to minus 4. So you'll get 1 equal to 0 plus b into minus 4. So hence b equal to minus 1 by 4. And we have to make this term as 0 for finding a. So I am going to put s is equal to 0 such that the b term will be cancelled out. So 1 is equal to a into 0 plus 4 plus 0. So from this we'll be getting a is equal to 1 by 4. So substituting this 1 by s into s plus 4 can be written as 1 by 4s plus minus 1 by 4 into s plus 4. So by taking inverse Laplace transform, we are going to get the y of t, which is 1 by 4 u of t minus 1 by 4 e power minus 4t u of t. So I am taking 1 by 4 outside. 1 minus e power minus 4t u of t. I'll write it clearly here. 1.4 1 by 4 is 1.25 into 1 minus e power minus 4t u of t. So this is the answer. So coming to the next problem, a second order control system exhibits 100% overshoot its damping coefficient is. So we know that percentage overshoot is given by m of mp, which is e power minus pi psi by root of 1 minus psi square into 100. It is given in terms of percentage. In our case, the overshoot is 100%. So of 1 minus psi square into 100. This 100 cancels out. We'll get e power minus pi psi by 1 minus psi square. Taking ln on both sides, we'll be getting minus pi psi by root of 1 minus psi square equal to 0. So from this, the psi is 0. So the answer is the damping coefficient must be 0 for the control system to exhibit 100% overshoot. Coming to the third problem, the transfer function of a second order system is 4 by s square plus 2.4s plus 4. They have asked to find the settling time. So we know that the general transfer function of second order LTI system, second order system is omega n square divided by s square plus 2 psi omega n s plus omega n square, where omega n is the natural frequency and psi is the damping coefficient. So by comparing this with the given input, given transfer function, 4 by s square plus 2.4s plus 4. So from this one, we can easily compare and write omega n square as 4 and omega n is 2 radian per second. And comparing the second term, 2 psi omega n equal to 2.4. So we know that omega n equal to 2 radian per second, and from this we'll be getting damping coefficient as 0.6. So It has been already derived that for 0, that is for a damping coefficient ranging from 0 to 0.69, the settling time is approximately given as 3.2 divided by psi omega n. So, which is 3.2 divided by 0.6 into 2. By solving this, we'll be getting 2.67. So, hence the answer is 2.67. Suppose psi is greater than 0.69, we'll be applying another formula for the settling time, which is approximately given as 4.5 psi divided by omega n. So for damping coefficient less than 0.69, the settling time is indirectly proportional to the damping coefficient. But for psi greater than 0.69, the settling time is directly proportional to the damping coefficient. Okay. So for our problem, the answer is 2.67. Thank you.